Hello, everyone, and welcome to my presentation on the development of wound care robotics. So, why do I care about wounds? Well, wounds are a critical public health issue affecting approximately 8.4 million people in the US for chronic wounds specifically, and wound care more generally costs the US healthcare system an estimated $126 billion. As you can see, this is also a global issue from the visual on the right. Wounds further disproportionately affect older adults, which is a very fast growing population, and this is compounded with a nursing staff shortage. Therefore, there is a need for alternative solutions. I believe that robotics can be an avenue to supporting nurses in wound care. However, in order to understand how robots can support nurses, we need to understand how wound care is done so we can translate it into applicable robot design that can improve nurse workload and patient care. So you may ask, are there currently any existing wound care robots? Well, there have been a few studies focusing on some wound care tasks, such as specifically cleaning surgical wounds or measuring wounds. However, there is not a full understanding of the actual needs within wound care and how robots can help. These studies do not focus on the perspective of nurses, whose input and opinion are critical to better understanding how robotic systems can help in wound care. I believe there is a need for foundational work on understanding the wound care process from nurses to create effective robotic systems. My study adds to this gap in the knowledge base. In my study, we observed nurses conducting wound care at a hospital and assisted living facility, where we took notes and categorized our observations into different relevant groups to inform robotic designs. These groups include things such as care steps, care tasks, grasping techniques, materials, and many more. Our findings from this study include the first wound care taxonomy from a robotics perspective, robot design recommendations, a wound care data set, a coding schema for the wound care data set to analyze it, and finally, we provide a case study showing how to utilize our design recommendations through the development of a wound care dressing robot. Here's our taxonomy we made from the ground up and is the first wound care taxonomy for robotics, and it outlines the interaction types, subject types, and tasks done by nurses during wound care. Another important finding from our study was pinpointing time-demanding care steps. We found that nurses spent most of their time setting up for wounds or dressing wounds. We decided to approach wound dressing as a case study to show how to utilize our design recommendations into a robotic system. More of our findings will be submitted for publication this year. These are the 6 design recommendations we extracted from our study specifically for wound dressing. From our study, we have recommendations for each wound care step and care task found in our taxonomy. As I go through my robotic design, you will see each of these robot capabilities inspiring our design decisions. Wound dressing requires the picking and placing of gauze using precision and non-prehensile grasping as seen on the figure to the left. The materials also need to be picked and pressed from the edge of the material to maintain sterility. We incorporated this into our design by using a roller mechanism as seen on the video to the right. This design uses hooks to pick up the gauze from the edge of the material when rotated clockwise, but then the hooks retract when rolled counterclockwise in order to press gauze onto a wound site without harming the patient. Here's a prototype of our roller mechanism picking up gauze in the real world. The hooks grasp onto the gauze, then the roller mechanism rotates and the gauze is lifted. This is our current roller design, the model design on the left and the 3D printed design on the right. Another requirement for the system is it needs to be able to conform to the curvature of the human body. Therefore, we introduced these side hinges, as you can see on the right images, made of flexible TPU material to allow for the roller to conform when a force is applied. This can be seen in our simulation here, where when a force is applied to the right, the roller displaces and conforms. Here's an example of our roller in the real world conforming to the human arm with the red line indicating it turning at different angles to conform to the curvature of the arm. Again, you can see an example of this as you move to the right side of the arm. And this is the final video of our full dressing process. The gauze is lifted, then moved to the wound care site. The gauze is then unrolled onto the wound site and covering the wound. Our next steps include making the roll. Our max angle of the roller currently is 25 degrees. We would like to make it 45, and implementing a taping mechanism to secure the gauze. I hope my work emphasizes the importance of interdisciplinary work and the need to incorporate stakeholders throughout the designing of robots. Thank you.